radiation, the oldest light in the universe. But again, this is just another of those photographs. On the right-hand side of the screen is a friend of mine, Robin Ince, who's allegedly a comedian. I always say to the audience, you can be the judge of that. But he's there. He says he's there as a professional idiot. And what he basically does is manage the Q&A. So we run a Q&A through Twitter, actually, in the venue. And so the show is different every night. Always interesting, and always particularly deep questions emerge in the second half of the show. Let's show you one more, which was on social media. This was a picture of the show. You get a sense of the scale of the screens, and we're not far off this screen actually in Singapore. And now the state-of-the-art LED technology. This was in Dublin, I think, just from someone's iPhone, in fact, a couple of weeks ago. So what is the show about, the theme of it? It starts actually with a series of quotes, which are some of my favourite quotes from scientists primarily that I've grown up with throughout the years. One of the central ones is a really interesting quote from Richard Feynman. And many of you will know Feynman, a Nobel Prize-winning physicist, but also, I think, a very underrated philosopher, actually. He wrote some quite powerful essays, including particularly an essay in the 1950s called The Value of Science, where he mused on, how thinking like a scientist can be valuable in the wider public sphere, politics, the way we organise our societies and so on. And there's a great quote in that essay which booms out at the start of the show. He says, "What then is the meaning of it all? What can we say to dispel the mystery of existence?" Now that's a strange thing, as I comment on at the start, for a scientist to say. I mean, there are questions which obviously fall within the domain of science. So not only simple questions, such as why is the sky blue, why are leaves green? And also deeper questions, such as did the universe have a beginning or is it eternal? How did life begin? And is it common or rare throughout the universe? These are questions that, whilst deep and we may not have answers, they obviously fall within the domain of science. But the question that Feynman posed there, what is the meaning of it all, does not seem at first sight to fall within the domain of science. And one of the frameworks of the show is to say, well, of course, I joke with the audience. I say, you're only paying about, £50 a ticket. I'm not going to tell you the meaning of life. It would be more than offensive than that. And I don't know, of course. It's a personal voyage that many of us go on. But the argument I make is when we're talking about the cosmology and the astronomy and indeed the biology, what we know about these deep questions which fall within the domain of science, those answers and the quest for answers provides a framework which is necessary. If we want to ask questions such as, what does it mean to be human? Then it is a prerequisite to know where we are in the universe, when we are in the universe, and how we came to be here. It seems self-evident to me. So all the way through the show, what I'm trying to do is remind the audience that these scientific observations and explorations of the universe can feed in, if we wish, as individuals, can feed in to much deeper questions that we all, I think, ask ourselves and try to explore. Some of the images that I use are, as I said, ultra high resolution. I also use images like this, which not so spectacular until you know what they are. This is the opening image of the show, actually, after the big introduction. And it's an image of the Earth-Moon system, which is beautiful in itself, two sort of fragile crescents against the dark of space. But it becomes more remarkable when you know that this was taken from Martian orbit by the Mars Reconnaissance Orbiter spacecraft. So it has a very long focal length camera, which is usually used to take high-resolution photographs of Mars. But on this day, it was swung around to take a picture of the Earth-Moon system. And another of the introductions, actually, another of the quotes I use in the introduction to the show, is from Scott Carpenter, who's a Mercury astronaut and a test pilot, an Air Force test pilot. But when he orbited the Earth for the first time back in the early 1960s, he wrote an extremely beautiful, poetic reflection on what that experience meant to him. And it's all the more powerful, I think, because this is not a poet. As I said, this is a test pilot. But he said that the Earth is a delicate flower, and it must be cared for, and we are mistreating it. And it was to reflect back in the 1960s when, I think this is before the famous Apollo 8 Earthrise picture, I think before environmentalism was really as powerful an idea as it is today. It's a long time ago. But even then, the act of elevating himself upwards and taking a wider perspective, which was forced upon him by altitude in that sense, it turned this test pilot into a poet, someone who reflected on the value of our planet. And again, one of the themes throughout the evening is that I want to say that that perspective can be physical. Pictures like this, I think, underline the fact that this planet is, as Scott Carpenter actually says, he says it's not terra firma, it's a delicate flower. Beautiful words. The act of raising yourself away and traveling away from the Earth shows you that, but also the intellectual act of considering the science of cosmology, I think, does a similar thing. One of the threads at the start of the show is I step out to make that point, that the sense of altitude and distance from the Earth. Actually, it's a paradoxical thing I often find about the Earth, that the further away you get from it intellectually and physically, the more valuable it becomes. The next step out, of course, from a planet in the solar system is a galaxy, an island of stars. I use images like this. They are incredible high-resolution images, and on the LED screens, you see this brightness of the stars, the black of space. This is a photograph which is put together by the European Southern Observatory of the Milky Way, but taken from all points around the Earth, from the northern and southern hemisphere. So it's a beautiful picture of the Milky Way across the entire sky. So the right and left of this image are photographs of the Milky Way from the northern hemisphere, and the centre, and as you can see, if you know a bit of astronomy, the small and large Magellanic Clouds, which I can get my laser pointer working, are there and there. So this is the southern sky, and the northern sky over here. You get a sense of the scale of a galaxy. 200 billion stars, perhaps as many as 400 billion. I joke, actually, that astronomers don't care about factors of 2. So between 2 and 400 billion stars. I could just shout.
Sorry about this. All right, testing. Okay.
There we are.
Hello.
How's that? Oh, good. Right, got another one. I also have a very large tech crew on my shows. 16 rather than 1. So what we now know from looking for exoplanets around distant stars is that most of these stars, but I'd say to first approximation, all of them have solar systems, have planets around them. The current estimates for the number of Earth-like planets in a typical galaxy like the Milky Way suggest that maybe 1 in 10 stars has a rocky Earth-like planet, the right distance from the star to support, potentially, to support oceans and therefore possibly life. That means that we estimate there are about 20 billion Earth-like planets in the Milky Way galaxy alone. Now, we don't see the structure of a typical galaxy in a photograph like this from within because we're inside looking out. So the next step out into the universe, and it's another excuse to show spectacular pictures, is to step out to some nearby galaxies. This is one of the unbelievable high-resolution mosaics from the Hubble Space Telescope of a galaxy called the Whirlpool, which is a very well-known galaxy to our amateur astronomers in the Northern Hemisphere, at least, because you can see it with a very small telescope, even though it's 30 million light years away. This photograph, by the way, is about 170,000 light years across. And the Whirlpool's interesting because it's an interacting galaxy. So it's a galaxy in collision with a smaller dwarf galaxy, which is on the right of the image, that sort of yellow blob to the right. And what you're seeing there is the gravitational interaction, the collision between 2 galaxies. Now, 30 million light years, one of our nearest neighbours. One of the centerpieces of the show are a series of graphic sequences that were put together with a company called DNEG. And DNEG are one of the famous, biggest movie graphics companies. I think they're in Singapore, actually, as well. What they're most famous for, in my mind, is the graphics for Interstellar. So I'll show you in a moment a simulation of a black hole, which is one of the centerpieces of the show. When I start talking about general relativity in the show, I want to talk about space-time, so we can talk about cosmology. I use black holes as an example.
But the next thing is another thing they did for me, which is very beautiful, I think. It's a fly-through of a data set called the Sloan Digital Sky Survey. So that's a data set to plot or map the positions of galaxies in the observable universe. So each point of light in this fly-through is the mapped, measured position of a galaxy. And what we did was we coded that database into the graphics software and plotted a fly-through through the universe. The size of the galaxies is enhanced, so you can see them. They would just be sort of sprinkles of dust on this distance scale across the universe. But the relative positions of them are as measured. And I think images like this and visualizations of data like this give you a sense of the size and scale of the arena that we're talking about. These surveys allow us to estimate the number of galaxies that are visible to us, possibly in the universe. It's called the observable universe, and that number is of order 2 trillion. So when we're faced about questions, as I said at the start, what is the meaning of it all, then one thing we have to know is that we're physically insignificant. The Milky Way galaxy itself is one galaxy amongst 2 trillion in the part of the universe we can see. The universe, we are very sure, extends way beyond that piece. But these visualizations, I think, really do start to bring that home, the size and scale of the universe itself. Now, I mentioned DNEG, the graphics company. So what they did, it's not well known, I think, but what they did for the film Interstellar with the director Chris Nolan is they didn't just build an artist's impression of a black hole. What they did was code the equations of Einstein's theory of general relativity, Einstein's theory of gravity, into the graphics software. Kip Thorne, the Nobel Prize-winning physicist, probably the greatest living theorist in the field of gravitation, did it. So he wrote the software with them. And so when you see a black hole in Interstellar, what you see is a simulation. It is not an artist's impression of a black hole. So what I managed to do was get that code and work with them. So one of the centerpieces of the show is a fly towards and then orbit around a black hole. And that allows me to talk about the way that space and time are curved, what would happen to me if the audience watched me approach the black hole and indeed cross the event horizon and fall into the region of no return, if you like, the region of space-time from which no information can escape, which is called the event horizon and the interior of the black hole. So we can talk about that with a simulation of what it would look like. So I'm going to show you part of that simulation now. I can't show you the full version because actually no computer will run it because it's such a high-resolution image. So we have to use a special piece of kit, which I don't have here. But let me show you a kind of a fly towards and approach. The only thing that's in the black hole's in the center now, so the camera's flying towards it. The only thing that's in the input is a flat star field, nothing else, and then the mass and the spin of the black hole, nothing else. So all that distortion as we fly towards the black hole, you see this kind of strange mixing effect and the stars beginning to be pushed outwards in the field of view. That is the predicted curvature of the light rays, following the curvature of space-time caused by the mass of the black hole. And we can sweep by the black hole and go into orbit around it. And I could spend about, I don't know, a lecture course talking about what that distortion is that you're seeing there. And we discussed some of it in the show. One of the interesting things, actually, it's going to stop now because we don't go into orbit around it in this preview. One of the interesting things, though, if I get my laser working, is this region here. So this is the event horizon of the hole. We've frozen now so we can see. This brightness around the event horizon is interesting. In the theory in Einstein's theory, what you see there is you see light rays from the whole 360-degree sky focused, in fact, an infinite number of times onto the edge of the event horizon. So that brightness is, you can see the stars out here and out here. This is the whole 360-degree sky, a map of the whole visible universe, actually, surrounding you, mapped onto the event horizon. So there are all sorts of interesting things that happen, and I discussed some of those. So that's our black hole. I shouldn't take too long with this preview. One of the things that I talk about is when we're talking about the meaning of it all, again, we go back to this theme. What does it mean to be human? One of the things we need to know is how likely it is that life is present on other worlds, or what's the probability of there being life beyond Earth in, let's say, a typical galaxy or even a solar system. The answer is we don't know. We only know of one world where life exists. But it is interesting to look at the history of life on Earth, because the history of life on Earth can potentially tell us something about the probability of finding life elsewhere. What's interesting about the history of life on Earth is that it arose pretty much as soon as it could, after the Earth had formed 4.5 billion years ago and the oceans formed, when the Earth cooled down after its formation. And we certainly have evidence that there was life present on Earth 3.8 billion years ago, and some evidence that it extends beyond that, maybe to 4 billion years. So that's pretty much as soon as it could. Now, if you think what life is, then life must be the transition from geochemistry to biochemistry. That's what we mean by the origin of life. Because you start with a world where there is no life after its formation, and on Earth you ended up pretty soon with a world where there was biochemistry. So we have an idea that essentially carbon chemistry gets more complex in the presence of what a physicist will call gradients, or temperature gradients, pressure gradients, alkaline and acid gradients, and so on. So this idea that there may be a sense of inevitability about the increasing complexity of carbon chemistry in an active geological setting, such as a young planet, is a hypothesis, but it can be tested, potentially, if we're lucky. So one of the sections of the show is to try to look at other places and explore what we know about other places where those conditions existed, and indeed may exist today. This allows me to show some images of Mars. Many of the images, most of them actually, from the Mars Reconnaissance Orbiter. This is a beautiful image of Mars, a geologically active region of Mars. It's called Tharsis, the Tharsis Rise, heavily volcanic. The large volcano you see in the middle of this image is Olympus Mons, which is the size of France, the biggest volcano in the solar system. So we know that Mars was geologically active. It had active geochemistry. We also know that it was wet at some point in the past. Certainly, 3.8 billion years ago, the same time that life was getting a foothold here on Earth, the conditions on Mars were very similar. In fact, even rather more benign, we think. So Mars is a planet that shared the same conditions as Earth when life began on Earth. So that may suggest that we might expect to find that life had begun on Mars. That's something we can test, and we are trying to test now. So we're looking for the evidence that life did exist on Mars, or perhaps evidence that it still exists, because we again have strong evidence that the water on Mars did not all escape to space. Some of it went underground. There's certainly ice on Mars, and we have reasonable evidence there are pockets of liquid water below the surface on Mars. So it is not beyond the realms of possibility at all that there are Martians today, or that there were Martians in the past. I also go on to discuss, I won't show you some of the images, but it is certainly true that on some of the moons of Jupiter and Saturn, in particular Europa, one of the big moons of Jupiter, and on the smaller moons of Saturn and Enceladus, it is true today that the conditions that we think may have led to the origin of life on Earth, which is liquid water in the presence of active geology, those conditions exist today on some of the moons in the outer solar system. So if that hypothesis is true, that there's some sense of inevitability about this transition from geochemistry to biochemistry, if we're lucky, we might be able to verify that by finding evidence of life on Mars or the moons of Jupiter and Saturn. That doesn't answer when we start to ask these questions about what it means to be human, the value or otherwise of humanity in a typical galaxy, a civilization in a typical galaxy. That does not answer the question, how likely is it that there are complex, multicellular living things? If we find life on Mars, it will be single-celled. There is absolutely no doubt about that, we're sure. But what we really mean when we say, when we ask questions such as, are we alone in the universe? What we really mean is, are there places where there's complex multicellular life, and indeed things that can think, atoms that can contemplate atoms, which is a rather poetic description of a human being, but it's surely true. Well, again, we only have one example of a world with a civilization. This is another of those spectacular pictures from NASA Earth observation satellites of Earth at night. I always say actually that to me, what's the most remarkable thing about our planet? It tends to be our instinct to say, well, it's the beautiful rivers and the forests and so on, the diversity of life on Earth. That's certainly true. But if you were an alien flying into the solar system from elsewhere, the thing you would notice in the solar system would be the city lights on this planet. That is the most surprising and interesting phenomena in the solar system. It is our civilization. So what do we know about the emergence of civilization on the planet? Well, if you look at the history of life on Earth and you look for the emergence of complex life and ask the question, when did it occur? When did complex life emerge? In the fossil record, there is no evidence of complex multicellular life beyond about 700 million years ago. You can use genetic techniques to look for mutation rates in genes, to look for, in particular, sort of genes that lay out a body plan called Hox genes. And there's some evidence that maybe those genes were present, let's say 1.2 billion years ago at most. So most biologists would claim that given what we know at the moment, there was no complex life on Earth until something like 1 billion years ago, give or take a bit, which means that it took around 3 billion years to go from the origin of life to the first complex multicellular creatures. Now that may give a sense that while simple life may be common across the universe, complex life may not. And we go back, I keep echoing back to that Richard Feynman quote, what is the meaning of it all? What is meaning? Right? Now that is a question that I have a view on, so I challenge the audience in these shows to see if they agree with me or not. My view is that meaning is an emergent property of the universe. It exists because life exists. In a universe without life, there is no meaning. That's my challenge. So that means that if it is possible that complex life and civilizations are very rare, some biologists, a biologist friend of mine at the University of Manchester, likes to say when you look at the Milky Way galaxy, so you look at this beautiful image of the arc of the Milky Way, he likes to wind astronomers up and say, well, given what I know about the history of life on Earth and the immense unlikelihood of getting complex life and then intelligent life and then a civilization, if you look at those 200 billion stars across the arc of the Milky Way, all there will be there is slime at best, as he likes to say to astronomers. He may be right. If that's true, and if what my challenge to you is correct, which is that meaning exists locally, it is a property of complex multicellular life and indeed a property of intelligence. And the Earth is the only planet in this galaxy currently where a civilization exists, then this planet is the only place where meaning exists in this galaxy at the moment. And I think that's an interesting, it's a challenging thought. It's put out there. I make clear to the audience in a science communication that this is my view, but it's a view that I think is worth taking seriously because it begins to build in, it begins, I think, it both enhances and mitigates the terror of cosmology. As the great Arthur C. Clarke said, there's only two possibilities. Either we're alone in this galaxy or we're not, and both of them are terrifying possibilities. I think it begins to suggest that whilst we are physically insignificant, undoubtedly, we may not be insignificant in the sense that we may be rare and therefore extremely valuable. And it's in those clashes of ideas, I think, that we begin to be able to explore better what it means to be human. It's a very difficult idea to bang those ideas together. A physicist would call them orthogonal, at right angles to each other. But all the way through the show, what I'm trying to do is set up that friction in the audience's mind so they can go away and talk about these issues later and form their own view. There's one more thing that I just want to say. One of the things I decided to do was to try and address a lot of the questions that I'm asked, which are very good questions, often actually from younger people in schools, which seem obvious and but very challenging. One of them, I'll just give you one example, which is that this is a photograph of the oldest light in the universe. It's called the cosmic microwave background radiation. So it's from a satellite called Planck, and it's a whole sky photograph, which is why it's presented like a sphere. And what it is if you think about astronomy and you think about looking out into the universe, let's say that I look at the Whirlpool galaxy, the light has travelled for 30 million years from the Whirlpool galaxy I showed earlier to our telescope. Therefore, we see that galaxy as it was 30 million years in the past. Now, the universe is 13.8 billion years old. So you could ask the question, can I look far enough out into the universe that I can see so far away that I'm looking so far back in time that I'm looking essentially at the Big Bang, at the origin of the universe itself? And the answer is almost. Within about 380,000 years of the Big Bang, you can see light from that moment. And this is that light. Now, I don't want to go into the detail because I'm probably overrunning horrendously anyway, but the point is that this is a photograph of the universe as it was very soon after the Big Bang, and it is a very different universe to the one that we see today. It is a universe without stars and without galaxies. It is almost a uniform blob of glowing gas, hydrogen and helium, virtually no structure. And so the question is, how do you go from a universe like this, which is essentially structureless, very close to the Big Bang, to a universe like this on the right-hand side of the screen, which has stars and planets and galaxies, complex structures so complex that some of those complex structured atoms can think. How do you do that spontaneously, according to the action of a few simple laws of nature? It is a very good question. And we have a broad understanding, not a deep understanding, but a broad understanding of how that can happen. And so one of the things I do is I do a little experiment. And the experiment is with a cup of coffee, but with the cream on the top and the coffee underneath. And this is actually an experiment down to a great cosmologist, a friend of mine called Sean Carroll, who's investigated these properties of systems like that in some detail for this reason. So if you think about the coffee with the cream on the top and the coffee underneath, that's what a physicist would call a highly ordered system. In fact, the jargon term is a low entropy system. It means that there are very few ways of organising the molecules of cream and the molecules of coffee such that all the cream sits on the top and all the coffee sits underneath. Now, the universe, we know, shortly after the Big Bang, for reasons that we don't fully understand, was an extremely ordered, low entropy system. And the universe today is a disordered, higher entropy system. So the universe is moving from order to disorder. Now, if you look at the coffee example, what you can do is you can introduce a long-range interaction into the coffee, which is a spoon. So you can drop a spoon into the coffee and give it a little kick. But what happens? Well, what happens is, of course, the coffee mixes up. It goes to a disordered, high-entropy system. But in the process, you get swirls of cream in the coffee. You get complexity in the transition from the order to the disorder. Now, in the universe, the analog is gravity, a long-range interaction. So what seems to be the case, this is almost certainly true, although the details we don't fully understand, is that the challenge, the hypothesis, if you like, is in going from a highly ordered universe at the Big Bang, and I said we don't fully understand the reason for that order, but it was highly ordered, to a disordered future state. You get an intermediate phase of complexity, and that's the phase that we're in today. So broadly speaking, we understand that. Now, what's interesting philosophically about that is it means that the phase that we're in today, the phase of complexity, is very likely, well, or certainly temporary. So it means that, for example, the age of starlight, the age of the universe when the stars shine, is temporary. This is a photograph, one of those great Hubble photographs again, of an area of the southern sky called Omega Centauri, globular cluster. It's probably an ancient galactic nucleus that collided with the Milky Way. I show this because it's a remarkable image. The stars are only about a third of a light year apart in this region of space. And you see stars at all phases of their lives. You see red giant stars, you see bright young blue stars, you see red dwarf stars, the very faint white dwarf stars which cover the image. So you see stars at every phase of their evolution. Now, because we understand the physics of stars, and we understand the physics of star formation in a typical galaxy, we can estimate how long the age of starlight is. So what is the time when all fusion in all stars in the universe that we can see will have faded away? And there's a time limit you can put on it. It's 10 trillion years. It's a long time in the future, but it is a finite time. And so the end of the show, one of the messages that we deliver through various means, and there's a beautiful poem that my friend Robin Ince reads as well, is that in principle, it seems that we cannot live forever. We cannot be immortal. The age of structure in the universe is like the age of the swirls in the coffee. It's a very similar physical system in some ways. It is temporary. And so, again, when we approach this question about what does it mean to be human, part of the discovery that we have to go, the journey we have to go on, must be to accept the fact that we are limited in time and we're limited in space, in principle. And in fact, the suggestion of this physics, if you think about it, is we exist not in spite of the fact that the universe decays, but because of the fact that the universe decays. And that's quite, I think, a powerful idea. So with that, that was a kind of summary of the way the arc of the show goes. As you see, it's kind of, I think, a mixture of a lot of cosmology. There's a lot of general relativity in it that I haven't talked about because I didn't have time, but I've tried to explain that, the black holes, the spectacular nature of the images. But underlying it all, I think, is an attempt to answer some of the deeper questions that I get asked a lot, and I give both the framework within which people can think, and I sort of hint at my view. My view, as you can tell, is that the message from the universe is that we are extremely fortunate indeed to exist within it, and we will not exist within it forever, and therefore we should enjoy it while we can. That's my message. So with that, thank you very much. And I think I've probably banged on for way too long, but I can answer some questions if there is time to answer some questions. So I think we've got a mic, or you can shout out if you have any questions about the shows or anything else.
Questions, you can raise your hands and we'll come with the mic.
Hello?
I think there's one up there as well. There's one there and one up back.
Hi,
Hello.
I just want to say, first thing, I'm a really big fan of your shows, so thanks. And so, would you say that we are, as human beings, kind of the universe's way of understanding itself? Kind of because as like a whole sort of, universe, we're the only complex, well, that we know of, complex life. So would you say that we are kind of the universe's way of understanding itself, Ronnie?
Yes, I mean, I think I did actually say that once. I think someone put it on a T-shirt somewhere. But I mean, in a sense, I mean, it's the one caveat I would give is that there's no sense in which the universe had to be that way. I think what's my view of what's happened here is that because complexity is probably an inevitable transitionary phase, given an ordered start to the universe, then it seems inevitable that somewhere a complex carbon chemistry will produce introspective collections of atoms like us, right? So in that sense, but it's one thing I would caution against is thinking that the entire universe that there's some kind of need to understand itself or something. I think that we're a local phenomena that exists for a temporary amount of time. But obviously, this idea of meaning, it's a very strange word and it's often misused. But I think it's self-evident that it exists in the sense that the universe does mean something to us. It's obvious, isn't it? So I think it's in that sense, but I'm often careful because you don't want to get into the Deepak Chopra level of drivel. So we've got to be careful about what we mean by the universe thinking. But yeah, I agree with your sentiment, which I think is the way your question was meant. I think it was Feynman who said, there's a beautiful poem he wrote in that essay, The Value of Science, in which he says something like, a collection of atoms that contemplates atoms. That's it. That's what we are.
Thanks.
There's a question there. Oh, we'll take your question in a sec.
Sorry, could you keep your hands?
Professor.
Hello.
Yeah, I know you through an astronaut, Leland Melvin. Yeah, he recommended me to you. And I just want to ask a question regarding the last slide, this one, right? You mentioned the red stars are the one that is like quite aged, and blue stars are the one that are quite new.
Yeah.
However, I have seen a similar picture in the books that I have read, and it shows that these are like red shift and blue shift. The rest are the ones that's coming in to us, and blue are the ones that move.
That would be galaxies. This is a very localized cluster of stars. It's called Omega Centauri. So these stars are not, on average, are not in motion relative to us. They're very small amount. So they're all in the same place, and they're all pretty much moving in the same way. They're orbiting around a bit, but what you're referring to is galaxies. So when you look at the large-scale structure of the universe, then you find that galaxies, the more distant they are, the more rapidly. Well, the best way to think about it is that as the light journeys across the universe from them. So let's say there's a galaxy that's the light has been traveling from it for 5 billion years. Then it's been traveling across an expanding universe for 5 billion years, and therefore that light is stretched. And so that's what's called the cosmological redshift. And you're right so the Andromeda galaxy is coming towards us. So very local galaxies, where the expansion of the universe is not so important, they can be coming towards us, so you'll see a blue shift. But in these stars, what you're seeing is just seeing red giant stars, which is what will happen to the sun at the end of its life. Or you're seeing very massive, bright blue stars. So there's no measurable, there's a measurable movement here, but you can't see it. It's a very small red or blue shift. Thank you. There's a question there, isn't there? I'm making the person with the microphone run from side to side, which is or actually, or I could, I'll tell you what, why don't you give
Testing.
I'll give you this one, so you can ask it. And then you can pass it back.
You said that we could see back to just after the Big Bang. So if we had a very, very powerful telescope, could we see the Big Bang?
That's a brilliant question. So the answer is no. And the reason is, I didn't explain what this was fully, so that's why it's a brilliant question. So if we go back in time, so this is 380,000 years after the Big Bang. So if we go back before that, the universe was much hotter and denser. And it was so hot that atoms couldn't form. So an atom is like a hydrogen atom will be a proton and a nucleus with an electron going around it. It was so hot that the electrons couldn't go into orbit around the nuclei. They were moving around too fast. And so then the universe before this time was what's called a plasma, which is a sea of electrically charged particles, so before the atoms formed. And that's opaque, so light can't travel through it. So you can't see further back than that, because the universe is so dense and all these charged particles that it's literally like looking at this solid wall. You can't see through. So as the universe cooled down, because it was expanding, at this point, then the atoms formed and the universe became transparent. And so then the light can travel through it. So this is as far back as we can see using light. Now, just to add something, which is something I mentioned in the shows, again I didn't talk about, but we've just detected recently, the Nobel Prize was awarded for the detection of ripples in the fabric of the universe itself. They're called gravitational waves. And they're a completely new way of looking at the universe. And so we see, for example, the collision of black holes using that technique. And that technique, in principle, if we had a big enough detector, could see back all the way to the Big Bang. You could see the ripples from the Big Bang, but not in light. So it's a great question.
Hello. Hi.
Where are
Over
you?
here. So I have a quick question. If the universe started as a singularity, right? The singularity is necessarily uniform. So I'm wondering what introduced the non-uniformity. I would think that the universe, if it started uniform, would continue to be uniform. There's nothing else that would disturb that uniformity.
Brilliant question. And the best theory we have for explaining that, these are
these are these colours. I didn't say again, but perhaps you know they're non-uniformities in the distribution of matter at this point, at the level of 1 part in 100,000. So it's almost smooth, but not quite, which is what these colours are. Now, the best theory we have to predict those, and it was a prediction initially in the 1980s, is a theory called inflation. So the idea is that before the universe was hot and dense, so it's before what we now call the hot Big Bang, we think space-time was there, if this theory is correct, and it was expanding exponentially fast, very, very fast indeed. In fact, it was doubling in the models. So if you take 2 points in that space, the distance between them doubled every 10 to the minus 37 seconds. So it's called inflation for that reason. And the thing that drives that inflation in the model is a thing called the inflaton field. And it has fluctuations in it, which are quantum mechanical fluctuations. And those quantum mechanical fluctuations in that field, when the inflation slows down and the universe heats up, are manifested as a fluctuation, density fluctuations in the distribution of particles in the young universe at the Big Bang or just through the Big Bang. Now, the interesting thing about that theory is that it predicts several things, but one of the things it predicted was this. And that was before, this observation of non-uniformity in this young universe was made in the late 1980s initially. And this is a very recent picture of it. But before then, this cosmic microwave background, which is what this is, was a uniform glow. But actually, a group, Stephen Hawking had a lot to do with this, actually. It's one of the reasons he's most well respected. There's a group in the early 1980s in Cambridge that predicted the fluctuations in density should exist in the young universe based on that model, and they got it right. Not only just the overall feature, but the detail of these fluctuations. So that's the best theory that we have to explain that. I should say that whether that universe had a beginning or not is interesting, because the Big Bang becomes an event in a pre-existing universe, which happened 13.8 billion years ago, which is the end of inflation. And if you just look at general relativity, and Hawking actually, and Hartle and others proved that there has to be a singularity in the past. But general relativity is known not to be complete. In fact, you need quantum effects in there. So it's not known whether the universe had a beginning. What we do know is that it was hot and dense 13.8 billion years ago.
Thank you.
Hello? You mentioned that...
Yes, good. Yeah.
You mentioned earlier that somehow we've managed to calculate that the universe is finite and that we've got, say, a 10 trillion year cap on it from now.
No.
Has there been any sort of prediction? Has anyone tried to hazard a guess as to what the end as such might look like? Or what happened after that?
Oh, so no, I didn't say it was finite. We I think if I was to guess, we don't know, but it's probably infinite in space and time. The point is, though, that the time when complex structures exist in the universe is finite. So space, as far as we can tell, so our current measurements are that space is not only continuing to expand and will expand forever, but is in fact speeding up in its expansion. And so we think the end point of the universe is a universe where, if you take 2 points in space, the distance between them will double every 20 billion years or so, and do that forever. It's called an exponential expansion. But what unless some physics intervenes that we don't understand, that universe will be essentially empty. And even the last thing to happen is that the black holes themselves that formed in the universe and exist in the universe today will evaporate away, as far as we can see. So we think the universe, the end point of the universe, if no new physics happens, is a universe that's just a uniform sea of radiation with no structure at all. So it's the structures that are temporary. But I could say there are, I mean, just to be fair to other theorists, there are models which can change that of new physics, essentially. So there are models in which the universe can recollapse because things change. But the baseline is that it'll just continue to expand forever. There was a question there, wasn't there?
What happens if
or somebody goes past the cannot come back line in a black hole?
That's a superb question, and I do talk about that in the show. So the first thing to say is you can go across it and not feel anything yourself, especially if the black hole is very massive. So you could dive into the black hole, nothing untoward would happen to you at all when you cross the event horizon, which is the point of no return. What would happen though eventually is when you cross that line, your whole future is at what's called the singularity, at the center of the black hole. So your time is limited inside the black hole, as far as we know. And so we don't fully understand we don't understand at all the very center of the black hole, but we're pretty sure that that's the end of time for anyone that crosses the horizon. So just as you have to go to tomorrow, so you can't stop yourself going to tomorrow. If you go across the event horizon of a black hole, you can't stop yourself going to the center, and you are what's called spaghettified. So you'd have the wonderful experience of being stretched a lot, and then ultimately you'd come to bits. This is basically what happened to you. So time would end for you.
Going on from the question just then, you said it would be the end of time, but how would that work, or how would that look?
It's again an excellent question. So and I haven't talked about it much, but Einstein's theory is a theory of space and time together. It's a thing called space-time, and so one of the things I do talk about is that what we know is that there's no such thing as absolute time, and there's no such thing as absolute space. So your time now is personal to you, so that literally the rate at which you age depends on the path that you take through space-time, which means it depends on the events that you experience, basically. So you will age because you're sat with your mum now, so you might go to school tomorrow, and she might go to work, and so you'll experience different events. And it really is true that means that you both age at slightly different rates. It's a tiny, tiny effect, right? But it's, we see it with atomic clocks. It's part of the satellite navigation system. We have to correct that effect, so it's a real effect. So one way of thinking about what's happening when you fall into a black hole is, in some sense, the time and space descriptions flip around. That's one way of thinking about it. So it really is true what I said to the person who asked the question before, that in the same way that you have to go into the future now, you have to go to tomorrow, you have to go to the center of the black hole for the same reason, essentially. So because of the way that space and time mix together. So you're asking the question about relativity, which is a cool thing. So if you're into physics, there are some great books you can read on relativity, which are not so hard, mathematically. So great descriptive books. But that's what you're interested in. You're interested in Einstein's theory of relativity.
Wonderful. Probably the last question, ladies and gentlemen.
There's one there, isn't there? That's the last question.
Sorry, you might
This is also about black holes. So, somebody once told me that a black hole is like a really small planet with a lot of gravity. And if that's true, how does that have anything to do with time?
So Einstein's theory of general relativity, which is what we're talking about, is it was initially a theory of space and time. It became a theory of gravity, and then became a theory of cosmology. So roughly speaking, what Einstein's theory says, what is gravity? So his idea is you can imagine space and time as a fabric. It's often called the fabric of the universe. And the idea is that when you put something into the fabric, like a star or a planet or anything actually, then it curves the fabric. It makes it warm. It's just like a sheet of rubber, right? So it's curving. So space and time are getting bent by the presence of matter, curved and warped. And then
the idea is that what gravity is the response. So you can imagine it almost like a little marble rolling around on the curved surface, and it will be deflected on the curved surface as seen from someone that's watching the marble roll about. And that's essentially Einstein's theory of gravity. So what you're seeing when you see the black hole is you're seeing a distortion. I can just play it once more because I'll show you what you're. If you look at this. What you're seeing visually here is the prediction of the paths of the light rays as we're moving a camera towards a black hole, and you're seeing the light rays. What the calculation that's being done is what path that the light rays take through this distorted space-time. Now, what we're seeing really is the distortion visually. You're seeing it as distortion in space, but it really is also a distortion in time. And I'll give you one example, which I give in the show, and we perform this on the stage, actually. If I were to walk towards that black hole now, so let's say as we go into orbit around it, it will freeze in this version of the thing, it will just sit there. So imagine that I started to walk towards the event horizon. What would you see? You would see time, for me, slowing down. So you would see my movement slow. You would also see the light from me get redder and redder. But in particular, you would see time slow and slow and slow. And if I decided to dive in, as the previous questioner said, and dive in across the event horizon into the region of no return, I would be able to do that. I would experience that, I would fall in, nothing strange would happen to me at all from my perspective. From your perspective, time is so distorted from your perspective that you would never see me fall in. So you would see time stop for me on the horizon of the black hole. So you would see my image sort of fading away forever on the event horizon of the black hole. Whereas I would just dive in and nothing would happen at all until I got to the middle. So that such is the distortion of time. But the answer to your question is that the theory itself is a theory of the distortion of space and time by the presence of a massive object. So, I mean, it's quite a difficult. It's one of the in the real show. We have more graphics, and I take about 20 minutes to talk about that, and I show exactly what's happening with the light paths and the ticks of clocks as you move towards it. So it's a superb question, and that's the quick answer I've just given.
Right, everyone, if you could join me and thank Brian once more. Also for your questions, we hope you enjoyed this special session made possible by our partners, Lateral Events. We hope that you will join us again for future events. Come back to Science Center and also tell your friends about Science Center. Show us some love and support. We will try our best to arrange more of these kind of events in the future. In the meantime, there is still time to interact with Brian and ask him any dying questions if you're very shy, typical of Singaporeans. Do join us outside for canapes and refreshments. We will see you outside. Thank you very much.